For Lab 6, we're going to be using the concept of projectile motion in order to help us calculate the velocity and the final position of the ball we're going to launch. We're going to be using 4 different degrees, from 0 degrees, 30 degrees, 45 degrees, and 60 degrees. And then we're going to also find the theoretical measure of them. This is important in the real world because we can use it to measure things like launching a basketball, or maybe what angle we need to shoot a bullet from in order we're like target practicing or things like that.
So for our next materials, we're going to be using these ones. We're going to be using a launcher, which is going to help us to measure the distance at a certain angle. We're going to be using a steel ball, which is the one that we're going to be launching. We're going to be using a piece of paper, which is going to help us to mark the landings of the steel ball. We're going to be using a carbon paper, which is going to do the work of marking the landings. And we're going to be using the ruler, which is going to help us to measure the distances. So for the first part of the experiment, we were in the need to launch a steel ball around 5 times with this launcher. The next step, when launching the ball needs to land on this paper so we can mark the dots of the positions of the ball.
Yeah.
So we already made the experiment, the steps, and we already have the dots, which are these ones, from the land positions of our launching process. And yeah, that's it. So for second step of our project experiment, we're going to be launching the ball at a 30-degree angle, and we're going to be using a second paper, and we're going to use our theoretical final position, and we're going to put a new paper in that position in order to start our new launchings and to start seeing where the ball is going to land.
So after launching the ball 5 times, we're going to be measuring each of them in order to get the average of the final position.
Esto no está haciendo nada efectivo, espérate, mejor están dando los...
1, 2, 3. Una, dos, tres. Oh, pensé que se iba.
So the first thing that we did was we got our first 5 attempts, which was just at 0 degrees, and it was 100.31 centimeters, 131.50 centimeters, 132.50 centimeters, 133.50 centimeters, 133.70 centimeters. And the average of that was 126.30 centimeters, which is 1.26 meters. So the first thing we did was find table 1 data to collect the muzzle velocity, and we had the x coordinate and the y coordinate. So the initial position for the x was 0, and for the initial for the y was 0.87 meters, and for the final position in the x coordinates 1.263 meters, and in the y 0 meters. For the initial velocity x was the value we needed to find. But for the velocity y, it was 0 meters per second. The acceleration on the x coordinate was 0 meters, and on the y coordinate, it was negative 0.98 meters per second squared. And the time was what we needed to also find. So to find the time, we needed to use the square root of 2yi, which is a 0.87 meters, divided by negative 9.8. And that was also times negative 1. And for the time, we got 0.42 seconds. After that, we needed to find the velocity, which is the Vm, and we needed xf, which is our 1.263 meters divided by 0.42 seconds, which we found previously. Our Vm was 3.01 meters per second. That was our muzzle velocity, and we will use it for the rest of the lab, which is Vx is equal to Vm, so 3.01 meters per second. So the next thing we did in step 2 was look for the Vx using a different angle, and for that we needed to use the Vm we found previously times the cosine theta of whatever angle we were using. So first we were going to do 30 degrees, and our Vx was 3.01 meters per second, which is what we found previously, times the cosine of 30, and that gave us 2.61 meters per second. And then we needed to find the Vy, which is the vertical, and we needed the Vm, which we found previously, times sine of theta. So that was 3.01 meters per second times sine of theta, so sine of 30, because it was the angle we were going to be using, and that gave us Vy 1.51 meters per second. And the next step, we needed to find our A, B, and C, which is our theoretical time, and with that we found that 1/2 times negative 9.8 gave us negative 4.9 meters per second squared, and B 1.51 meters per second, C 0.87 meters per second. And with that, we calculated it on our website, and our x2, which is our theoretical time, was 0.603. And we found that using negative b plus or minus square root of b squared minus 4ac divided by 2a, and we just plugged in the values that we had before, negative 4.9, 1.51, and 0.87, and that gave us 0.603 seconds, which means that we got it correctly the first time. So the next thing we did was find the theoretical final position for each angle that we were going to use, 30, 45, and 60. So for 30, we did Vm cosine theta times the time that we just got, and that gave us 3.01 meters per second cosine 30 times 0.603 seconds, and that was 1.57 meters, and that was our theoretical final position for the angle 30 degrees. So in our first attempt, we got 1.572 meters, 1.585 meters, 1.590 meters, 1.590 meters again, and 1.595 meters. And we got the average of that, and it was 1.586 meters. Our percent error we did was using the theoretical final position minus our experimental position, and it was 1.57 minus 1.586 divided by 1.586 again from the average times 100, and we got a percent error of 1%. For the next angle we did was 45%, again using the same formula of Vm cosine theta times time. We got 1.28 meters as our theoretical final position in 45 degrees. So our first attempt, 1.482 meters, 1.491 meters, 1.499 meters, 1.505 meters, 1.509 meters, and our average was 1.50 meters. And then we used that to calculate our percent error again, and our percent error was 14%. Now doing the same thing for 60 degrees, Vm cosine theta times time was 0.91 meters, and testing that out with our experimental values was 1.232 meters, 1.232 meters again, 1.241 meters, 1.242 meters, and 1.244 meters, and our average was 1.24. And we calculated the percent error again using 0.91, which is our theoretical final position minus our experimental final position divided by our experimental final position again times 100, and that gave us 26%. And finally, this is just table 3 landing theoretical values and percent error for different angles, and in 30 degrees and 45 degrees and 60 degrees. So for 30 degrees I got 1.57 meters, which is our theoretical distance, which was calculated before. Our experimental differences, which is just the average, 1.586 1.86 meters and our percent error, which was 1%. And then for 45 degrees, we got the theoretical distance of 1.28 meters and our experimental differences of 1.50 meters and our percent error of 14. And then finally for 60 degrees, we got 0.91 meters for the theoretical distance, 1.24 meters experimental differences, and percent error of 26%.
So for conclusion, we're going to answer some questions related to the experiment. For the first question we have, where do the percent errors come from? They come from two main values, which is the theoretical distance and the experimental differences, which is the average of the distances from our launching attempts. For the last question we have, are all the percent errors equal or not? In this case, they're not equal, and that's because mainly of the fact of the calculations from the theoretical distance, which might give us a different value from the average between the experimental launching distances, and that might be the case why the percent errors differ that much. For the second question, do you think that there are factors that are affecting the experiment that we're not considering in the formula? Yes. Which ones? Well, maybe it's not in the main formula, but it could affect the whole process of our experiment, which is the drag force. When we're launching the steel ball from the launcher, the ball is in the middle of the air, and when something is in the middle of the air, there's a force opposing the motion, which is the drag force. Is this value significant? In this case, it's not, because comparing the drag force from a bigger object, the drag force will be more significant. So that's why we don't include the fact of the drag force in this formula, because as it's such a small object, it won't affect the experiment that much. For the next question we have, do you think there's a way to minimize the error? There might be one way to minimize the error, which is take in consideration the drag force in the whole experiment. In conclusion, we learned how to predict the landing of a projectile at different angles.
Hi, my name is Alexandra, and I helped measure all of the points.
Hi, my name is Ilan, and I set up the experiment. I made some of the procedures and the conclusion.
Hi, my name is Gabby and I did all of the calculations.
Hi, my name is Itzel and I recorded and edited the video.